Welcome back to the Algebra 2 series. This is the third video in a series of videos about the rational roots of polynomials. And in the last video, I addressed the idea that we would try to isolate a root of this very difficult cubic equation. And in doing that, I had originally written 24 and then 30 and tried to determine the number of possible rational roots. Of course, 1, 2, 3, 4, 6, 8, 12, 24 from the numerator portion, and then 1, 2, 3, 5, 6, 10, 15, and 30 from the denominator portion are going to give us all kinds of fits when we try to do this by synthetic division. I think in this case that trying to attempt to factor this is out of the question as well. It's just an absolute beast as a problem. So we're going to use a technique called isolation in order to try to solve this out, and hopefully we will be able to do that in short order. The first thing we're going to do then in synthetic division, writing the 30, negative 49, negative 10, 24, we're going to notice that almost all of our techniques fail in this case because, for example, the numbers 30, negative 49, 10, negative 10, 24 do not alternate nicely. It's hard to determine whether a positive or negative number would work. So what we're going to do here is we're going to list out just the numerator values first. So we typically write out plus or minus 1, 2, 3, 4, 6, dot, dot, dot. Now, we rarely get to these larger numbers, so I'm just going to put a dot, dot, dot there. The first thing I'm going to notice is that if you add up the coefficients, we end up with a positive 30, a positive 24, and two negative numbers that add up to a value greater than, an absolute value greater than 54. So our remainder, if we plug a 1 in there, would be negative. And I'm going to write that negative right above there, because that's going to be important for us to know. Again, we're looking for sign changes between these roots. So naturally, I would want to try something simple. I'm going to try the number positive 2. It doesn't matter if you try a positive or negative. I think you're going to find that both of them are similar in this way. So let's try the 2. Bringing the 30 down, that gives me a 60 here, which would be 11. Then 22, or 11 here. Oh, excuse me, that's 12. Um, can't seem to add today. There we go. And then a 24. And it's interesting to note that this became 24, but that's simply a coincidence. And the number 2 doesn't give us a clue. We didn't make a mistake. Oh gosh, there's a 24. We're just wishing, oh gosh, I wish this was a negative 24, but it wasn't. But what we do notice is that the answer is positive, and so we put this right up here, and all of a sudden we see, aha, we've got a sign change between 1 and 2. And that is critical because that gives us our big clue as to what type of value could work here or could produce one of our final roots. So I go to my selection of fractions, and I'm looking for fractions between 1 and 2. So I see I have 3/2, I have 4/3, 6/5. As you can see, there are plenty of them. 8/5. We have a lot of possibilities here. We have also, okay, so that's far enough. I don't need to do more than that. I'm going to start with the simplest of them, and that would be 3/2. And I'm going to test 3/2, and I'm going to see, again, I'm looking right up here. I'm looking to see what happens when I put 3/2 in. Will it give me a plus or will it give me a minus answer? And that will be able to help me isolate where my answer lies. So here's what's going on. On the on the on the graph, we have 2 and we have 1. And we know that the answer here produced a negative, and the answer here is a positive. So I'm going to pick the number right in between. And let's say that I find out that my remainder is positive. Then I'm going to pick something in this little interval here and see if I can isolate it further. I'm going to try to narrow it down until I nail that one value I'm looking for. So let's take a look at that. I'm going to try something like the 3 halves and see how that works. So bringing the 30 down, multiplying by 3 halves is going to be 45 because I'll cancel the 30 with a 2 and then multiply by 3. So that makes 45. So negative 4 is when we add. Multiply again is going to be negative 6, it looks like. And then negative 16 cancels 8 times 20. Oh, 24. So we do get the negative 24, which was what we hoped would happen. We would get a 0 here. Boy, it makes us just extremely happy because it only took us essentially 2 tries in order to get the one value that works. Now, of course, we're not going to continue with synthetic division because, as you can see, we now have 3 terms here, which indicates a quadratic. But I do want to show you one other trick that we tend to use for this. We're going to bring down our first answer, which would be x minus 3 halves. And then the second part would be 30x squared minus 4x minus 16. Now I'm going to do something called jump a factor. Jumping a factor is factoring out a common term out of here and jumping it over into the other binomial. So the common term is 2. So if I take a 2 out of these guys, that would be 15x squared minus 2x minus 8. And jumping that 2 into the other binomial gives me 2x minus 3. So it makes everything look much more pleasant. I have what I'm hoping is a factorable quadratic here, and I'm going to be an optimist and say, yeah, I think that's going to factor 2x minus 3. And we know that by our prime factor method, we can simply take the 8 and the 15. We will go ahead and prime factorize these guys. And quickly, we should be able to determine what our factorization is if we get any. We want a middle term of 2 by subtraction, and in this case, we want to separate our 2. So I kind of see it popping out at me right here. I've got a 12 and a 10. 12 minus 10 is 2. So we'll finish this out by writing a 4 here and a 2 over here. That comes from the 2 top parts, and then the 4 goes with the 3. So 3x here and 5x right there. In order to determine the actual signs, we're going to have a minus 12 and a positive 10 to make the negative 2 in the middle. Anyway, so that was a separate part of this, but we have to get down to the quadratic, and once we get to there, we see that. Now notice what the other answers would have been. There were no easy answers in this problem. We end up with 3 halves. We end up with 2/3, that one being negative, and we end up with 4/5, that one positive. These would have been the only 3 terms that would have worked. Now, in the previous example, I want to point one other thing out here. You might think, well, what if there was a bigger number that worked? Well, I want to show, though, that when we found this positive, keep in mind that originally, when you find something that has a positive answer, look along this bottom line right here. And if all the numbers are positive, then none of these values are going to work. So I think you're going to find that in this problem that was also the case. But what we avoided, what we ended up avoiding was we ended up avoiding having to deal with all the other possibilities there. And that's the trickiest part. So before I finish this video out, I want to just cover one more thing, and I'm going to just move away from this one to another one. Here it is here. And I want to just show you one last little trick. And just to list out, and I know there are plenty of fractional possibilities here, but just to take the number 10 and write those out, there would be 1, 2, 5, and 10. And one of the things I wanted to show was that if you take a look at the numbers 6, negative 25, 21, and 10. They do not alternate because of the 10 at the end. However, there's a clue that shows you that the first 3 terms do alternate. So when the first 3 terms alternate like that, then you're not going to want to choose a negative number. Let me illustrate what I'm talking about. I'm going to take negative 2 and put it in there. You're going to immediately see what happens here. This becomes 6 and then negative 12. And then negative 37, and you see how this is very quickly exploding. 74, 95. Obviously, you're going to get a negative number here, but it's never going to be this small. So what we see is that sometimes you can see a pattern right from the beginning, and if they begin by alternating, we're not going to want to choose a negative number. Likewise, if the numbers, for example, if I had a 4, 5, 16, and a negative 6, then these numbers do not alternate at the beginning. They're all the same, and so I would not try a positive number. Instead, I would try a negative number over here. And what that does is it forces the alternation as we work our way down the isolation or through the synthetic division. So what I wanted to show today was one more of our little properties or one of our little hints, and that's this part right here, where if you see an alternation in the first three numbers, then you're not going to want to try negative numbers. And if likewise, if you see no alternation between them, then you would want to try some negative numbers to force that alternation to come in. I hope that helps get us started in this. These are very difficult synthetic division problems to find these rational roots, but it can be exciting when you finally nail it.